Good morning everyone. This is AP Mishra, Senior Lecturer of Physics from Sri Chaitanya Gosala campus. As we have entered the final phase of preparation for the NEET examination, so today I am going to discuss previous year question of magnetism and matter. So without wasting a time, let's move to the questions. Okay. So the first question which we have to discuss is a uniform conducting wire of length 12A and resistance R is wound up as current carrying coil in the shape of, so you can see that they have given two different shape. First, they are saying that that wire has to be wound in the shape of equilateral triangle which will have a side A, and the second shape in which we have to wound that wire is a square which is having a side again A. So two different shape, and for both what we have to do, we have to calculate magnetic dipole moment of the coil. Okay, and they have given I as the current which is flowing through each coil. So you can see here that as they have given the total length 12A, but the side length for both the coils they have given A. So the total length, if I take here triangle, equilateral triangle, so for the equilateral triangle, the side length is taken as A. So what will be the total length we have? The total length will comes out to be what? 3A. But here the total length is given what? 12A. What does it mean? It means that this wire is not having a single turn. It has a multiple turn. So since it has a multiple turn, so what we have to do? We have to calculate that number of turns in order to calculate the magnetic dipole moment. How we can do that? So we know total length we have is how much? 12A, and we will equate it with the number of turns into the length in single turn. What will be the length in single turn for the equilateral triangle we have? It will comes out to be what? 3A. It will be 3A. So if you cut this A both side and we can also cut this 3 both side, what will be the final value of N we are getting? Number of turns for triangular coil we are getting is what? It is coming out to be 4. It is coming out to be 4. Once we got the number of turns, what we will do? We will calculate the magnetic dipole moment for it. How we can calculate? So you can see that magnetic dipole moment formula is what? It is NIA. It is NIA. So what is the number of turn we have? That number of turns we got is what? Here we can take this magnetic dipole moment 1 because the first shape we got is what? Triangle. So we have to calculate for 2. So that's why let's take this as M1. So M1 value is equals to what? N. N value we have is what? 4 into I, which will remain as it is, into A. What will be the area of the triangle? Area of the triangle will be half into base. What will be the base of this equilateral triangle? It will be A. And what will be the altitude? Because half into base into altitude is the area of triangle. So what will be the area of triangle we will get here? So that altitude we have is what? You can see that this angle we have is 60 degree. So if we want to calculate this altitude length, it will comes out to be what? A sine 60. A sine 60, which means it can be written as root 3 by 2 A. So that I will write here. So it will comes out to be what? Root 3 by 2 into A. Okay. So this will be the value we are getting. Now, in this case, you can see that we can cancel this 4 with these 2. Okay. So we have 2 2's and this 4, 2 into 2, 4. This 4 is getting cancelled. So what is left with us? So we have now finally the value. So magnetic dipole moment for the triangular coil we are getting is what? It will be root 3 I into A square. Root 3 I into A square. So that will be the answer we have for the triangular coil. Okay. I hope you have understood that. So in that you can see in these option, any option which is giving you the answer root 3 I A square. So you can say there is only one option, which is the option number B. In that they have given one option where we have root 3 I A square, and we don't have any other option in which we are getting this option or this value as an answer. Okay. So what we can do, this can be marked directly as a answer, but we can verify if you want, although it is clear that B is the correct answer, but you have to if you want to verify, For the square, that also you can do. So let's quickly calculate for the square. If we want to verify that what will be the dipole moment we have for the square, okay, so that we can do. So we will quickly calculate that also. So there is a square coil. If I take, and the side length for that square coil is given what? It is also given A. It is also given A. So now what will be the total length we have? Total length we have is 4A. What is the total length? Total length is a 4A. So once we got this, now the wire length we have is 12A. So now what we have understood from there, that there will be a multiple turns in this coil. Okay, so what will be the number of turns we have, that we can calculate. So number of turns, if we want to calculate, how we can calculate? So for that you can simply take total length, which is 12A, that you can equate equals to what? Number of turns. So last time I have taken N, so this time I am taking N dash into 4A. So after that you can see that this A is going to be cancelled both sides, and this 4 and 12 also is getting cancelled. So here we are getting 3. So what will be the value of N dash we are getting? Finally, the N dash value we are getting is 3. What will be the value we are getting? 3. Okay. So now we are going to calculate the magnetic dipole moment. So magnetic dipole moment relation we have is what? We know it is NIA. So here I am taking N dash. Current in this coil also we have is what? This coil also has a current I. Same as the previous one. Okay. So now A is the area. So we can take this also as A dash, because last time we have taken A. So we can write here N dash, which is 3, and I. What will be the area of the square? Area of the square will be 4, not 4, sorry, A square. It will be A square. So you can see that the magnetic dipole moment we got is what? It is 3I A square. So now you can see that we got both values. For triangle also we got the magnetic dipole moment, and for square also we got the magnetic dipole moment. And what will be the correct answer we are getting? Root 3I A square. We had the dipole moment for what? It was a dipole moment for triangular coil. And 3I A square we got a dipole moment for what? For the square coil. So I hope you guys have understood that. Okay. So what is the correct option we have? Correct option is B option. B option is a correct option. So let's move to the next question. Okay. So now we are going to solve the second question. What is that second question? So second question is a wire of length L. A wire of length L meter carrying a current I. So again you can say the current is given what? I. And the length of the wire we have is what? L. Is bent in the form of circle. So this coil is bent in the form of circle. Its magnitude of magnetic moment will be equals to what? What will be the value of the magnetic moment, magnetic dipole moment? Again, we have to calculate that. So how we can calculate? Basically, in this question, they have given that there is a wire, and that wire is being converted. It is being converted into a circular coil. So that wire is converted into a circular coil. Okay. So what will be the dipole moment we have if there will be a I current which is flowing through it? So let's say I current is going to flow through this. So since it is a circular coil, so this circular coil will also have a radius. So that radius we have to calculate. Let's say that radius we have is what? Small r. And the length of this straight wire was given what? L. So we know that the total length of this circular coil will be what? It will be its circumference. So we can simply equate the circumference of this coil, which is 2 pi r. Okay. With the total length of this wire, which is L. So from there we can get what? We can get the radius. We can get the radius, and radius will comes out to be what? L divided by 2 pi. L divided by 2 pi is the radius. Once we got the radius, we can calculate the magnetic dipole moment, which will be NIA. Okay. But here in this case, the coil do not have multiple turns. It has only single turn. So you can take that N value as 1. Okay. So we will write here 1, and the current we have is what? I. And what will be the area we have? That area we have is what? L divided by 2 pi. Sorry, this we have area will be pi r square, because it is a circular coil. So we can write here pi r square. So we can write here I into pi into r value we have is what? L by 2 pi whole square. So after solving this, what will be the final answer we are getting? So the final answer we will get is what? It will be equals to pi L square I divided by 4 pi square. And in this case, you can say we have 1 pi in numerator and 1 pi in denominator. So we can cancel these values. So 1 pi from the numerator will get cancelled. So still there is 1 pi which is left in denominator. So what will be the final answer we will get? The final answer will be, final answer for the magnetic dipole moment will be what? It will comes out to be L square I divided by 4 pi. Okay, that will be the answer. So let's check in this which one is having the same answer which we have got. So you can see the B option. Here we have I L square divided by 4 pi. Okay, what will be the unit we have for the magnetic dipole moment? It is ampere meter square. You can see from the formula, current unit is ampere and area will be meter square. So its unit will be ampere meter square. And what is the correct option? It will be the B option, which is the correct option. I hope you understood that. Okay, so B option is a correct option. So let's move to the next question. Okay, so now the next question which we have to understand is a 250 turn rectangular. So here you can say in this question the number of turns of the coil is given what? 250. Okay, and the shape of the coil is rectangular coil which is having a length 2.1 centimeter. What will be the length it has? 2.1 centimeter. And they have given width. What will be the width? They have given 1.25 centimeter, which is the width. Okay, and it carries a current 85 microampere. What is the current it has? 85 microampere. Okay, and it is subjected to a magnetic field which is having a strength 0.85 Tesla. So this is the magnetic field strength we have in which that coil is kept. Okay, what they are asking us to calculate? They are asking us to calculate work done in rotating that coil. How much? 180 degree. How much? 180 degree against the torque. Okay, so who is applying torque on that coil when it is kept inside a magnetic field? It will be a external magnetic field which is applying a torque on that coil. Okay, so we have to, if we want to apply the torque externally, so we have to work against the torque applied by the magnetic field. Okay, so here what will be the way of calculating it? So basically here you can see that whenever we have a coil which is being rotated, whenever there is a coil which is kept inside a magnetic field and that coil is rotated by a certain angle, so the work done we can calculate. That work done can be calculated by using this simple formula. What is that formula? That formula is M into B cos theta 1 minus cos theta 2. Okay, so where M is what we have? M is the magnetic dipole moment of the coil, and B is what we have? This is the external magnetic field which is applied on the coil. And what is theta 1? Theta 1 is the initial angle. As they are saying that the coil is rotated by an angle 180 degree, so we can take the initial angle to be 0 degree, which means initially we can assume that it is having a orientation parallel to the magnetic field. Okay, so theta 1 value we can take 0 degree, then you can take directly theta 2 value, which is the final angle which that coil is making with respect to magnetic field, 180 degree. 180 degree. So now let's calculate first M. What is the M value we have? So M value we can calculate how? It can be calculated simply by using NIA. Okay, and B value is given to us. What will be the B value we have? It is 0.85 Tesla. N value we have is 250. N value is 250. I we have is what? It is 85 microampere, which is 85 into 10 to the power minus 6. Okay, and what will be the area we have? Area is length into width because it is a rectangle. So what will be the area we have? Area will comes out to be what? 2.1 into 1.25 into 10 to the power minus 4. Why I kept here minus 4? Because this 2.1 is in centimeter as well as this 1.25 is also in centimeter. So both quantities are in centimeter. So we can convert it into meter by simply multiplying it with 10 to the power minus 4. Okay, I hope you have understood that. So now let's substitute these value in this work done equation. So what will be the final answer we will get on substitution? So you can see that the work done will comes out to be 250 into 85 into 2.1 into 1.25 into 10 to the power minus 6 into 10 to the power minus 4 and the magnetic field value which is 0.85 and Then we have to substitute the angle, these theta values. So we know that theta 0, when we substitute the theta 1 value 0 degree, so theta 0 degree is what? It is 1, and theta 180 degree is what? It is minus 1. So what we can write here? We can write here 1 minus of minus 1, 1 minus of minus 1. Okay, after substituting all these values, what we will get? The final answer. The final answer we will get is, it will comes out to be 9.4 microjoule. 9.4 microjoule. The answer will comes out to be 9.4 microjoule. So here you can see, is there any option we have in this? 9 point, which is equals to 9.4. This is actually approximate answer. 9.4 is an approximate answer. Okay. So what will be the answer we have? Yes, there is one option, that is A option. So what will be the correct option in this particular question? It will be A. So A is the correct option. So next question which we have to discuss is, a bar magnet is hung by a thin cotton thread in a uniform horizontal magnetic field, and it is in equilibrium state. The energy required to rotate it by 60 degree. Energy required to rotate it by 60 degree is W. Now, the torque required to keep the magnet in this new position is. So, what will be the value of the torque which is required to keep that magnet in that particular position? Okay. So, that is what we have to calculate. So, basically, you can see that there will be, they are saying that we have a bar magnet. There is a bar magnet, and that bar magnet is kept inside a horizontal magnetic field. Okay. And this bar magnet is making an angle 60 degree. How much angle it is making? It is making an angle 60 degree with respect to the magnetic field. With respect to magnetic field, how much angle it is making? 60 degree. So when the magnet, the bar magnet is at this position, so at that time it is experiencing a torque due to external magnetic field. So when it is experiencing a torque due to external magnetic field, so in order to hold this magnet at that particular position, we also apply a torque externally, because if we don't apply the torque externally, what will happen? Under the influence of the torque due to magnetic field, it will again try to come back to its initial position. Okay. So that's why to keep it at that position, we have to apply the same amount of torque which it is experiencing at that particular position where it is making an angle 60 degree. I hope you got this. So now quickly we can calculate that. So simply you can say the torque which we have to apply externally, that should be equal to what? The torque which it is experiencing because of the magnetic field. Because of what? Magnetic field. So that we can equate to M into B sine, what is the angle it is making? 60 degree. Okay. But in order to calculate that torque, you can see that we require the value of M into B. But we don't have that. They have not given us the value of magnetic dipole moment as well as the external magnetic field. So how we can calculate it? Okay. And you can see the options in that they have given the option in terms of W. So we can do what? They have given a very important information that the energy, the torque, the energy required to rotate that magnet by 60 degree was what? It was W, which means you can say what is that energy? Whatever the work we have done in order to rotate it from its initial parallel position, parallel to magnetic field position to this position, that will be considered as what? Energy required to rotate it. Okay. So we can use that again, that formula. What is that formula? It is W is equals to what? It is M into B cos theta 1 minus cos theta 2. Okay. Again, theta 1 value we have is what? What is theta 1? Theta 1 value is 0. What will be theta 2 value? Theta 2 value will be 60 degree. Theta 2 value we have is 60 degree. So let's substitute that value. We will get what? M into B cos 0 degree minus cos 60. Cos 60 value we have is 1 by 2. Cos 0 is 1. So 1 minus 1 by 2 will give you what? It will be MB 1 minus 1 by 2, which will comes out to be what? MB by 2, which will comes out to be MB by 2. So that will be the work done we are getting, or W value we are getting. But we require what? We require the value of M into B. So from there we can calculate what? We can write this M into B, which will comes out to be what? 2 times of W. 2 times of W. So that we can use here. This we will substitute where? We will substitute it here. So that will give you what? That will give you the final torque value. So what will be the torque which has to be applied? That torque will be equals to M. In place of MB, we are writing what? 2W. Sin 60 is what? It is root 3 by 2. So again you can see that we have here, we have to cancel this 2 because 2 is present in numerator as well as in denominator. So we have cancelled it. So what will be the final value we have got? The final value we have got is the external torque is equals to root 3 times of W. This is the final answer. You can see, let's check any answer, any option which has this. So you can see A option is root 3 W by 2, B 2W by root 3, which is also not correct. Then we have third option which is W by root 3, and then finally you can see the fourth option which is root 3W. So that is the correct option. That is what we have, correct option. Okay, so D is the correct option for us in this particular question. So let's move to the next question. Okay, so the next question which we have to understand is, following figure shows the arrangement of bar magnetism in different configuration. Each magnet has magnetic dipole moment M. So you can see that each magnet is having how much? It means all the magnets which we are taking, they are having a same dipole moment, that will be M. Okay. Now, which configuration has highest net magnetic dipole moment? Okay. Which configuration among them has the highest net dipole moment? So you can see we have 4 different configuration. Here you can say these 2 magnets are perpendicular to each other, and here you can say one magnet is kept, both magnets are kept anti-parallel to each other. Okay, how? Because you can see that their opposite poles are together. Okay, and then we have the orientation in which they have 30-degree angle between them, and then we have 60-degree angle between them. So out of these 4 configuration, which one is going to give you the highest net magnetic dipole moment? So you can see that quickly one by one we are going to calculate. So let's say here you can say we know the direction of magnetic dipole moment is from south pole to north pole. So in this case, if you take, this will be the magnetic dipole moment for this magnet, and for this it will be here, and both are having how much angle? 90 degree. Okay. So when we have 2 perpendicular vectors, how we calculate its net value? So in this case, you can say the net value we are getting is what? This M net value will comes out to be what? It will be under root M square plus M square. Under root M square plus M square. So final answer we are getting in this particular situation. What will be the net magnetic moment we are getting? So net magnetic moment value we are getting is root 2 times of M. Okay, root 2 times of M, and we know that root 2 times of M can be written as 1.41 times of M. So that will be the value we have. After that, we can see this configuration. So in this particular configuration, we have magnetic moment opposite to each other. One is in this direction, one will be in this direction, and since both magnetic moments are in opposite direction and their magnitude is also same. So in that particular case, the net magnetic moment value we are getting is what? What will be the net magnetic moment we will get? 0. What will be net magnetic moment? 0. So once we got the net magnetic moment 0, let's move to the next one. So here in the third C part, you can say they are making what? They are making an angle 30 degree between them. So in this case, if we apply the net magnetic moment formula, so M net value in this particular case will comes out to be what? It will comes out to be M square plus M square plus 2M square, because it is M1 into M2. So directly we can get as M1 and M2 both are having same value. So it is 2M square cos 30, and cos 30 is what? Root 3 by 2. So what will be the final value we are getting? It will comes out to be what? You can see that we can take M square is common in all, that we can take outside. So finally inside the root we have got is 2 plus root 3. 2 plus root 3. Okay. And if we calculate this value, so approximately that value will comes out to be 1.9 times of M. Approximately it will comes out to be 1.9 times of M. Now the last one we have to check, and then we will be able to tell which one is having the highest magnetic moment. So the last part we have is what? Or last magnet you can see we have, in that the orientation is 60 degree. Okay. So you can see this will have a magnetic moment here, and this will have a magnetic moment here, and the angle between them we have is 60 degree. So what will be the net magnetic moment we have? So M net value we will have is, M net value is equals to how much? Let's calculate quickly. Again here M square plus M square plus 2M square cos 60. Cos 60 is 1 by 2. So we will get m square, m square, m square in each term, and when we add them, we will get root 3m, and root 3m can be written as 1.73 m. So you can see, if we compare all the magnetic moments, which configuration has the highest? It is C, that configuration where the angle is 30 degree, where the angle is 30 degree. So you can see the highest configuration we have, a highest magnetic dipole moment we have when the angle between the magnets are 30 degree. Okay, I hope you have understood that. Okay, so what will be the correct option we have here? The correct option we have is C. I hope you got that. So let's move to the next question. Okay, so now the next question we have, a bar magnet of length L and magnetic dipole moment M is bent in the form of an arc. As shown in the figure, the new magnetic dipole moment will be. What will be the new magnetic dipole moment we will have? Okay, so this is the question they have given us. So how we can calculate that? So in this particular case, whenever there is a magnet, basically here you can say initially we had a straight bar magnet. Okay, and that bar magnet was bent in the form of arc. So when we are going to, and initially its magnetic moment you can take M. Now when it is bent in the form of arc, it is making an angle 60 degree. What is the angle it is making? 60 degree. So when it is making an angle 60 degree, so in that particular situation, what will be dipole moment it will have in this particular case? So you can see that when we take the dipole moment, it will be a shortest. Okay, always you have to draw it along the shortest length between the poles of the magnet. So the magnetic moment, new magnetic moment which I am taking here, M dash, that will be from this pole to this. If I consider this as south pole and this as north pole, what will be the value of this? So the value of this new magnetic dipole moment because of the bending will be equals to what? It will be 2m sine theta by 2. How we can calculate? 2m sine theta by 2 divided by theta, where theta is the angle that arc is subtending at the center, and that is given what? 60 degree. That is given 60 degree. So we can substitute that 60 degree angle. So but carefully you have to remember that 60 degree you cannot substitute as it is. You have to convert it into a radian. Okay. So what will be the value we are getting here? M dash we are getting is 2 into m sine theta value we have is what? It is 60 degree. So 60 by 2 will comes out to be what? 30 degree. So sine 30 degree divided by this theta has to be substituted in radian, which will be theta is 60. 60 means pi divided by 3. That will be the value. Okay. So what will be the final value we are getting? Sine 30 we have is what? 1 by 2. So we will get here 2m sine that sine 30 we have, that we can write as 1 by 2, and that 3 pi by 3, this 3 will move to the numerator and we will divide entire value with pi. So next you can say we have to cancel this 2 with 2. So what will be the final answer which we have? The final answer we will get is 3m divided by pi. So that will be the final answer. So what you have to remember? You have to remember this relation, and you have to also remember that theta has to be, this theta which we have has to be substituted in radian. If you are going to substitute that degrees, you will not get the correct answer. Okay. So what will be the final answer we have? So out of among all these options, which one is the correct option? So we have C option, which we got as an answer. So C will be the correct option. Okay. So C option is the correct option. So let's move to the next question. So now we are going to discuss one more problem here. That problem is a magnetic compass needle which is allowed to move in a horizontal plane is taken to geomagnetic pole. Okay. Then what will happen? They are saying that we have a magnetic compass needle. Compass needle, you know, which is used for identifying the direction. Okay. And it is also a small bar magnet. Okay. So that we are taking where? We are taking it as taking it to a pole, geomagnetic pole. So what will happen? How it is going to react when it is being taken to a pole? That is what we have to understand, or that is what we have to answer in this particular question. Okay. So one thing which we have to remember, that at poles, when we are going to move to a pole, then in that case, the vertical component of the earth magnetic field will be equal to its total value. Whereas, which is a very important point, the horizontal component will be 0. We don't have any horizontal component at pole. So when we don't have horizontal component of Earth at pole, so if the compass needle is allowed to move in horizontal plane, then it do not have any magnetic field in horizontal direction. So in horizontal plane, it will not experience any kind of torque. So it will remain in the position, whichever position it had before reaching to the pole there. Okay, so it means wherever, whatever position you will keep it in the pole, that position it will maintain throughout. Why? Because it is not experiencing a torque. So what should be the correct option here? So you can see that they are saying it will stay in north-south direction only, it will stay in east-west direction only, it will become rigid showing no movement, will stay in any position. It will stay in any position, because if I change the position, then whatever position of that magnetic compass I maintain, it will have that position. Okay, so manually you can change its position. Okay, but whatever position it will have, that will be the position it is going to maintain. Okay, because it is not interacting with the horizontal component as it is not present. So which option is the correct option? It will be D option. It will be D option. So next question we have a bar magnet having a magnetic moment of 2 into 10 to the power 4 joule 2 into joule Tesla inverse. Okay, so that will be the magnetic moment value we have for a bar magnet, and this bar magnet is free to rotate in horizontal plane. In which plane? In horizontal plane. A horizontal magnetic field is applied. What will be the value of that horizontal magnetic field? 6 into 10 to the power minus 4 Tesla. Exists in a space. The work done in taking the magnet slowly from the direction parallel to the field to the direction 60 degree, which means initially that bar magnet was kept parallel to magnetic field. It was kept parallel to magnetic field. Okay, and then slowly that magnet is being taken to a position where it is making an angle, 60 degree with magnetic field. This is what we have, external magnetic field. So now what they are asking us to calculate, what will be the work done, what is the amount of work we have done in order to move it. So I hope you remember this equation, work done equation, that is m into b cos theta 1 minus cos theta 2. So what will be the value of theta 1? So theta 1 value, if we write, theta 1 value was 0, theta 2 value we have is 60 degree. Okay, and they have also given the magnetic moment, which is 2 into 10 to the power 4, and magnetic field 6 into 10 to the power minus 4. So let's substitute that value. So we are getting here 2 into 10 to the power 4 into 6 into 10 to the power minus 4, and here we will have cos theta 1, which is 1, because theta 1 value we have is 0, minus cos theta 2, which is 60 degrees. So here we will get 1 by 2. Okay, so 1 minus 1 by 2 will give you what? 1 by 2. So if we cancel this, so 10 to the power minus 4 and 4 will get cancelled directly. So we will get here 2 into 6 into 1 by 2. So 2 and 2 you can cancel. So what will be the final value of work done we are getting? That value will comes out to be what? 6 joules. So that will be the answer. And you can see that option is given, B option. What is the option we have? Where we have 6 joule? That is B option. Okay, so B option is the correct option. So let's move to the next question now. So in this particular question, they have given that two bar magnet having same geometry with magnetic moment M and 2M are firstly placed in such a way with their similar poles. Are on the same side. They are at same side. Then its time period. In that situation, the time period of oscillation of that combination is given T1. Now the polarity of one of the magnet is reversed. It means we are going to change the south pole and north pole direction of one magnet. Because of that, the time period of oscillation becomes T2. First of all, we have to understand here, whenever you can see, quickly you can see that if suppose we have a magnet which is kept inside a magnetic field, okay, if this magnet is going to start oscillating, then the time period we can calculate by using this relation, which is T equals to 2 pi under root I divided by M into B. What is I? I is the moment of inertia, M is the magnetic moment, and B is the external field in which that magnet is oscillating. Okay, so now what is the situation given to us? The situation is given that we have two magnets which are kept together with their same poles together. Okay, so in that case, the magnetic moment of these two poles are in same direction, which means if we calculate the net magnetic moment, so that will comes out to be what? It will comes out to be m plus 2m. So that will give you the total magnetic moment 3m. And since the geometry of these magnets are same, so we can consider their moment of inertia to be same. So what will be the moment of inertia we will get if we consider here the moment of inertia of both as I1 and I2, that I am taking equals to I. So what will be the total moment of inertia we are getting? I total value we are getting equals to what? It will be 2I. It will be 2I. So what will be the time period of oscillation we have? So time period we will get for this combination that is given as T1. So what will be the value of that T1? T1 value will comes out to be what? It will be equals to, that T1 value will be equals to 2 pi under root total moment of inertia, which is 2I, divided by net magnetic moment which we have calculated, that is 3m into B, because magnetic field is going to remain, we have taken that external magnetic field value B here. Okay, now the second situation which they have given in this question is what? That now one of the magnet polarity is reversed. Let's say the first magnet polarity is reversed. So we are taking here south pole and north pole, and here we have north pole and south pole as it is for the second magnet. So because of that change in polarity, what we have now, the magnetic dipole moment of both are going to be reversed, and because of that reverse magnetic dipole moment, what will be the net magnetic moment we are getting? M net value we are getting is what? It will comes out to be 2m minus m, which will give you what? Finally the value m. So what is the net magnetic moment we are getting? M. What will be the moment of inertia total value? So it will not change. It is going to remain what? 2I. Why? Because moment of inertia is a scalar quantity. It doesn't matter which direction you are going to keep the magnet. Okay. So the total moment of inertia is going to be simply added. It will remain 2I. So what will be the T2? What will be the time period of oscillation we will get? It will be coming out to be 2 pi under root. Again, you can say 2I divided by m into B. Okay. So now here you can see that from this T1, we can replace what? We can take this 2 pi under root 2I by mb. That I can replace with what? This I can replace with T2. When I will replace it with T2, what is left with us? It is root 3, which is going to be there. So if I write here the equation finally, which we will get, so that final equation we are getting is what? That T1 is equals to what? It is T2 by root 3. And from there, if we further solve it, we will get that T2 value will equals to what? It will be equals to root 3 by root 3 times of T1, which means that the time period in second case will be higher than the time period in first case. What will be the situation we have here? So in this case, you can see that which option is correct. So the first option, which is giving you the time period of second case is greater than the first case, that is only the correct option. Okay. So this A option is a correct option for us. Okay. So I hope you have understood that. So let's move to the next question. So now the next question, in that question, what is given to us? They have given an iron rod of susceptibility 599, which is subjected to a magnetizing field, and the value of magnetizing field is given what? 1200 ampere per meter. The permeability of the material of rod is given, is to be calculated. Permeability of the rod or of that given material has to be calculated. They have given permeability of free space, which is 4 pi into 10 to the power minus 7. Okay. So how we can calculate that? So first of all, we have to understand this, that what is the relation we have between the relative permeability and the susceptibility. So relative permeability is equals to 1 plus susceptibility. This is the symbol of susceptibility, and we can substitute the value here 1 plus 599. What is the value of susceptibility we have? It is 599. So what is the value we are getting finally? It is 600. And we also know that mu r is equals to what? It is equals to mu divided by mu naught. Mu is the magnetic permeability in a material. Okay. And mu naught is a magnetic permeability in a free space. So what we can write here? We can write here mu value is equals to what? Mu r into mu naught. What is the value of mu r? That value we got is what? 600. And mu naught is 4 pi into 10 to the power minus 7. 10 to the power minus 7. So what will be the value finally we will get? So if we multiply here 4 into 600, which is 2400 pi into 10 to the power minus 7, and we can also write it in terms of 2.4 pi into 10 to the power minus 4. So that will be the final answer we have. And this, now you can see, and what will be the unit we have? Unit will comes out to be what? Tesla. Unit will be same as the unit we have for this mu naught. What is that? Tesla meter ampere inverse. Okay. Now, where out of all these options, which one is the correct option? So you can see that the correct option we have is what? C option. We have got the exactly same value. Okay. So that is what we have, the correct option. Okay. I hope you have understood that. Okay. So now the next question which we have is what? A thin diamagnetic rod is placed vertically between the poles of an electromagnet when current in the electromagnet is switched on. Current in the electromagnet is switched on. Then the diamagnetic rod is pushed out of the horizontal magnetic field. Hence, the rod gains gravitational potential energy. What it has gained? Gravitational potential energy. The work required to do this comes from basically what has happened. There was a diamagnetic rod which was kept in between the electromagnets. The moment we have started the current flow, because of that, the electromagnet started generating magnetic field, and because of that, what has happened? Because of that, the diamagnetic rod has started moving vertically. Okay. So what was the, basically what was the basis of movement here? Okay. Which quantity is responsible here for the movement of that rod? That is what we have to find or tell here. So you can see that electromagnet has started working when we have supplied current. If we don't supply the current, there will not be a magnetic field which is being generated, and if there is no magnetic field, no movement of this diamagnetic material will happen. So the basis of this movement is what? It is the current source which is supplying that current. Okay, because without this, it is not possible to move that diamagnetic material. Okay, so what is the correct option here? Correct option is A. What is the correct option? A is the correct option. Okay. So I hope you have understood that. So let's move to the next question. The magnetic susceptibility is negative for which material? Okay. So we know that magnetic susceptibility, basically magnetic susceptibility, how we can calculate. If we see for this diamagnetic material, generally the magnetic susceptibility is negative for diamagnetic material. But why it is negative for diamagnetic material? Quickly we understand. So we know the answer that it will be diamagnetic material. But why? So you can see that if I take a diamagnetic material and I keep it inside an external magnetic field. So if I keep it inside an external magnetic field which is having a direction towards right side, so there will be an induced magnetic field. So let's say the external magnetic field we have is B0, and there will be an induced magnetic field Bi, which is there inside the material of diamagnetic, and the direction of that induced magnetic field will be opposite to external magnetic field. So what will be the net magnetic field which we have inside that diamagnetic material? That net magnetic field value we have is what? It is B0 minus Bi. So this will be the net magnetic field we have. Now we know that mu r, relative permeability value we have is what? It will be mu divided by mu naught. And if we multiply and divide these two value with H, so we will get what? Mu H divided by mu naught into H. Okay, and mu H represents what? It represents the net magnetic field present inside the material. So inside the material, the net magnetic field is this, and that value can also be calculated by using mu into H. So we can write here B net. Can we write B net divided by B external, because mu naught H is what? Mu naught H is representing the externally applied field. Okay. So now in this case, you can see we know that B net value. Now the net value is what? From this net value, how we are calculating? By subtracting the induced field from the external field, because the direction of induced field is opposite. So the net value will be what? It will be smaller than the external field. So from there we can say that mu r value is what? It will be less than 1 because denominator is higher. Is it? And we know that mu r is also equals to what? Or we can simply say the susceptibility directly, if we try to calculate, it will be mu r minus 1. And you can see mu r is less than 1. So when we are going to subtract a quantity which is less than 1 from the quantity which is 1, so the final value we are getting is what? Susceptibility value we are getting is negative. So that's why the susceptibility of diamagnetic material will be negative. I hope you have understood the basic here. So what will be the correct option? It will be A, which is the correct option here. Okay. So now the next question which we have to understand is, there are 4 lightweight rod samples A, B, C, D separately suspended by thread. A bar magnet slowly brought near to each magnet or each sample. Sorry, not magnet, each sample. The following observations are noted. What are the observations which was noted? That A is feebly repelled, which means there will be a small repulsion observed in A. B is feebly attracted, there will be a small attraction in the B. C is strongly attracted. D remains unaffected. So what is the meaning of that? So here quickly we can understand. Basically here we have 3 types of, how many magnetic materials we have? 3 types of magnetic materials we have. First one is diamagnetic material, second is paramagnetic, third is ferromagnetic. So the diamagnetic material will be feebly repelled in the external field. So this A is representing diamagnetic material. B is feebly attracted. Which magnetic material is feebly attracted in the presence of external field? It is paramagnetic material. So this will be a paramagnetic material. And C is strongly attracted. So ferromagnetic material is the material which will be attracted strongly in the presence of external field. So this will be ferro. And D remains unaffected. It means it is a non-magnetic substance. It is non-magnetic. It is what we have, non-magnetic. So now you can see out of these 4 options, which one is the correct option? C is diamagnetic. No, it is ferromagnetic. D is ferromagnetic. No, D is non-magnetic. A is non-magnetic. No, A is diamagnetic. And the last one we have is what? B is paramagnetic. Yes, B is a paramagnetic material. Okay, so what is the correct option? D option is the correct option we have. Okay, so the next question we have is, if a diamagnetic substance is brought near to the north pole or south pole of bar magnet, it will be. So basically what we have to remember, that diamagnetic material in the presence of external field, it doesn't matter which pole is generating that field, whether it is north pole of the magnet or south pole of the magnet, it doesn't matter. In both the cases, whenever there is an external field, then diamagnetic substance is going to be repelled. So what will be the correct option here? That the diamagnetic substance is going to be repelled by both the poles of the magnet. Understood? So B option is a correct option. So next question we have is what? Nickel. Nickel shows ferromagnetic property at room temperature if the temperature is increased beyond Curie temperature. Then it will show what? So first of all, we have to understand what is Curie temperature. So basically Curie temperature is what? Curie temperature is a temperature above which the ferromagnetic substance will start behaving as paramagnetic substance. So what they are saying, that nickel is showing ferromagnetic property. So if the temperature of that nickel substance becomes more than the Curie temperature, then it will start showing paramagnetic properties. Understood? So what should be the correct option here? D option, paramagnetic property. That will be the correct option. Okay, paramagnetism. So D option is the correct option. Let's move to the next question. If magnetic dipole moment of an atom of diamagnetic material, paramagnetic material and ferromagnetic material are denoted by these symbols, mu D, mu P and mu F respectively. So what will be the values we can write? So understand one thing here, that at atomic level, the magnetic dipole moment for the diamagnetic material, which is mu D, that will be what? It will be 0, because at atomic level the diamagnetic material do not have any dipole moment. Why? Because the diamagnetic behavior is shown by the substance which has paired electrons, and when we have paired electrons, one electron is going to move in clockwise and second is going to move in anti-clockwise direction, because of which the net dipole moment they are generating is 0. Okay, so at atomic level we don't have any dipole moment for the diamagnetic material. Okay, so for diamagnetic material we don't have any magnetic moment, whereas if we talk about the paramagnetic material as well as we talk about the ferromagnetic material, both are having a non-zero dipole moment at an atomic level. Okay, so this is a small concept you have to remember. So based on that we can answer this question. So you can see first option is given, mu P is 0. No, paramagnetic cannot have a atomic level dipole moment 0. Mu D is non-zero, that is also not possible. Mu D is non-zero. Again, C option again is not possible. Now you can say D option, mu D is 0 and mu P is non-zero. So that is the correct option. So D option is the correct option we have. I hope you have understood that. So let's move to the next problem quickly. According to Curie law, the magnetic susceptibility, according to Curie law, the magnetic susceptibility of the paramagnetic substance at an absolute temperature T is proportional to what? So simple Curie law, if we talk about the Curie law, so according to Curie law, the susceptibility of paramagnetic material is inversely proportional to what? Inversely proportional to the temperature. So among all these, the C option is a correct option. Which option is correct? C option is a correct option. Okay. So next question we have is a diamagnetic material in a magnetic field moves. So they are saying that we have a diamagnetic material, we are keeping it inside a magnetic field. So in which direction its movement will be? So they have given these options. So we are going to choose from stronger to weaker part of the field, from weaker to stronger part of the field, perpendicular to the field, none of these. Perpendicular to the field, none of these. So the correct option we have is what? First of all, we have to understand here when we have a diamagnetic material. Let's say I am taking here a magnet. Let's say this is north pole of the magnet and it is generating a magnetic field. Okay, this is an external magnetic field which is being generated by this pole of the magnet. Okay, and in this case or in this, we are going to keep a diamagnetic material. This diamagnetic material is kept inside this external field. So what will happen here? So we know that diamagnetic material behavior is what? It gets repelled in an external field. So it will start moving in this direction. Is it or not? And you can see that near the pole we have strong field. Near the pole we have strong field. And away from the pole we will have weak field. So where the movement of this diamagnetic material we have? Diamagnetic material is moving from strong magnetic field region to weak magnetic field region. So what is the correct option? From stronger to weaker part of the field. It means A option is the correct option. A option is the correct option. I hope you have understood that. Okay. So let's move to the next question. For protecting a sensitive equipment from external magnetic field, it should be, they have given these options. We have to choose among these. They are saying that to protect the sensitive equipment, sensitive to what? Sensitive to external field. Okay. So how we can protect them? If we place it in an aluminium can, then will it get protected? If we place it in iron can, will it get protected? If we wrapped with insulation around it, when passing current through it, will it get protected? Surrounded with fine copper sheet, will it get protected? So among all these four options, which one is the correct option? So the correct option is it has to be placed inside iron can. Why it should placed inside iron can? Because iron can is, or you can say iron is what we have, it is a ferromagnetic material. So when we have a ferromagnetic material, so ferromagnetic material has what? Its permeability is very high. Its permeability is very high. So whenever we have an external field, whenever we will have an external field, so all those external fields are going to pass through the ferromagnetic material. So if we are going to keep any substance inside this which is sensitive, so that will remain unaffected because the maximum field is going to pass through the material itself. Okay, the cavity in which we have kept that sensitive material, it will remain protected. Okay, and why that field is going to pass through this material? Because of very high permeability which ferromagnetic material offers. Okay, so the correct option we got is what? It is B option. Okay, so I hope you guys have understood all the questions which I have discussed today. Okay, so with that I am going to wind up this session. Hope you guys have liked this. If you have liked this, please share it with your friends and do subscribe our channel. Okay, thank you.